going to talk about for the next couple minutes, it's only going to take us about 5 minutes, is talking about what are called similar solids. So we've talked about similar triangles. We talked a little bit today earlier about similar rectangles, right? We also have similar solids, meaning three-dimensional figures can be similar to each other as well. The same type of rules apply. The fact that corresponding angles are going to have to be congruent, and corresponding parts have to be proportional. Okay, so if I want to see if these two cones are similar, I just need to compare their corresponding parts. So I'll go left to right again. I'll do radius to radius. So it would be 8 to 5. I want to compare that to the height, which would be 15 to 12. I would compare that to the slant height, which would be 17 to 13. Okay, so I just need to check those ratios. So 8 divided by 5 gives me 1.6. 15 divided by 12 gives me 1.25. So really, I could stop here, right? It doesn't really matter about the last one. 17 over 13 gives me 1.307 and so on. I'll run that to 3.1. But nonetheless, they're not in the same ratio, so these two figures, these two solids are not similar. Okay, so I just want to kind of throw that out there. Now, one of the powerful things about similarity is that we can start comparing figures themselves and parts of their figures. So I can compare, like the lengths, if these two cones were similar, I can compare the length of the radii and then determine volume from that. Okay? So today what we're going to do is we're going to look at how those similar figures kind of interact with each other, and then on Monday we're actually going to solve for the missing volume or the missing surface area, that sort of thing, without having to use a volume formula or use a surface area formula. All right, so here's what you need to know. When you have similar solids, one-dimensional lengths, two-dimensional measurements, and three-dimensional measurements all have a ratio. Okay, so if two similar solids have a ratio, like a measurement of A to B, then their area is going to be a ratio of A squared to B squared, and their volume is going to be in a ratio of A cubed to B cubed. Okay, so first let's talk some vocabulary. What things would be length? What things would be one-dimensional? Okay, so this would be circumference, perimeter, a radius, a side, a slant height. Okay, so anything you can basically measure with a ruler. That would be a one-dimensional measurement. Anything that is two-dimensional is going to be area related. So opposite area, surface area. The other one that we haven't really talked about, but you've actually calculated, is called lateral area. So when we calculated surface area, we found the area of the bases and we found the area of all the sides of the figure, and we added them all together, right? The area of all the sides, not including the bases, is called lateral area. Okay, but the key word there is area, because it says area is two-dimensional. Finally, volume, that's obviously going to be volume. But it also could be weight. Weight is considered a three-dimensional measurement. All right, so just that's the vocabulary for each dimension, okay? Now, what I want to do is kind of explain a little bit how these dimensions work and how we go from one ratio to the other. Okay, so I'm just going to go down here. So keep in mind, this is one-dimensional, two-dimensional, and three-dimensional, right? If I know that, let's say we have two spheres, okay? Let's say that their radii are in a ratio of 1 to 2. The surface area of those spheres are going to be a ratio of 1 squared to 2 squared, or 1 to 4. The ratio of the volume of those two spheres is going to be in a ratio of 1 cubed to 2 cubed, or 1 to 8. Okay, so we're just talking about the ratios of their volumes, the ratios of their surface areas, the ratios of their, in our case, radius. It's in the radii, okay? So what if I have a prism whose side lengths are in a ratio of, let's say, 2 to 5. Okay, what about the ratio of their lateral areas? It would have to be squared and squared, right? So it would be 4 to 25. Okay, what about the ratio of their volumes? I would need to cube this. I need to cube my one dimensional. So 2 cubed is 8, 5 cubed is 125. Okay, I could also though, so every time we started there at one dimensional, I could start with 2 dimensional as well. So what if I said that we are in a ratio of 9 to 16? That's 2 dimensional, so that is a squared and b squared, right? So I would need to go backwards to get a to b. What would that be? 3 to 4. But I would then need to cube it to get my 3 dimensional. So what's 3 cubed? 27. What's 4 cubed? 64. Good job. What if I gave you the 3 dimensional? What if I said it's in a ratio of 8 to 125? I need to go back to one dimensional. So remember, this is a cubed and b cubed. So I have to take the cubed root. So what number times itself 3 times gives us 8? 2. And then, oh, I just did it again. Sorry. I should have made it up in my head, huh? Right up here. All right. So for your homework, what you're going to do is you're going to fill out a table like this. Okay. So scale factor. Is that a 1-dimensional, 2-dimensional, or 3-dimensional? That's 1. How about slant height? How about space area? 2D, and then surface area, and the volume. Okay, so you're going to work up and down. So here, if this is 1-dimensional, this 1-dimensional measurement must also be 1 to 4. If I want to go from 1D to 2D, I need to square it. So it'll be 1 to 16. Same thing here. My volume, then I would need to cube my original. So it'd be 1 to 64. Okay. This homework is on Google Classroom. Yes.
First homework, so we're mentioning like each column is different.
It's its own problem. Yes. Each column is its own problem. So I gave you in Google Classroom, I gave you categories here, and they're just drag and drop boxes. You don't have to type anything in. It honestly should take you less than 3 minutes to finish. It's very fast. Okay, then on Monday, we'll take this idea and use it to solve for areas, volumes, surface area, that sort of thing. Sound good? All right.